Today, I want to discuss something that I just recently discovered within the last month or so. The story has to do with desmos, derivatives, and Taylor series. Now, I'll immediately say that it would be helpful to the explanation if you knew what Taylor series is. But I feel like just knowing the derivative rules for trigonometric functions, exponentials, and exponents would be just enough. Specifically, I want to discuss how you can use patterns in derivatives to create formulas for finding a certain higher order derivative, and I'll explain what that is in a bit. Okay, why should you even care about this? Taylor series are used throughout math and science in order to express certain things in a way so that they can be dealt with differently. Not only that, but by the end of this, I hope you will see how derivatives have a beautiful pattern to them, showing that they are not random at all, but rather they express a deep, unapparent connection to the way they behave and their nature. Alright, so the story starts off with me exploring Taylor series. If you don't know what it is a series of terms that tries to approximate a non-polynomial function, like 1 divided by x, using a polynomial, which make things look cool and can be dealt with differently. The approximation has to be rooted at a point, and what gets cool is that when you change the points, the entire approximation changes. The more information or terms the polynomial has, the better the approximation. It has a complicated formula, and if you don't understand it at all, don't worry about it, since that is not what the video is about. All that you need to know for this video is that it requires knowing the nth higher order derivative of a function, which is what this symbol stands for. In case you don't know what an nth higher order derivative is, it is just what happens when you take the derivative of a function n times. So for example, a third derivative of a function is what happens when you take the derivative of it, then take the derivative of that, then that, so in total 3 times. There are many ways to write it, the easiest being like this. Taylor series looked interesting, so I wanted to automate it with any function. So I turned to desmos. Desmos has derivative support for the Newton and Leibniz notation. One slight catch: it does not include support for an nth derivative. In other words, you have to specify the higher order derivative, whether it was the first, second, or third, etc. Unless you like typing the Taylor series by manually finding the nth derivative yourself, this is no fun. Unfortunately, I pretty much gave up until a few days later, where I wondered, is there another way I can find an nth derivative of a function, maybe using a formula? For example, if I gave you a function, and if I wanted to find the nth higher order derivative of it, could I find an actual formula using n that gives you the nth derivative? And this is where the ideas came rolling in, and where our journey begins. We will tackle 3 functions: exponentials, sine of x, and finally 1 divided by x. The ideology will remain the same with all 3. Notice a pattern with their derivatives, then make inferences and identify the pattern specifically, then to derive a formula for it. We will start with the easiest one, exponentials. To tackle this, we use the first step in the ideology: find the pattern. For this, we don't want to find the pattern in the graph, but in the actual derivative itself. This is actually very easy. The derivative of an exponential, k to the x, is itself times the natural log of the base, k. If you want a quick reminder why, this is because when you change that base to be in terms of the number e, you can use the chain rule to get this, since e to the x is its own derivative. Now, we have to take the derivative of that. Well, remember, the derivative of a constant times the function is the derivative of the function times that constant. Since the natural log of any number, in our case k, is always a constant, then when taking more and more derivatives of k to the x, this natural log will accumulate. We can write this very neatly. The nth derivative of an exponential is itself times the natural log of the base raised to the power of the derivative you are taking. And boom, that's the formula for the nth derivative of an exponential. Using this, we can write the Taylor series for this on Desmos, and it looks kinda cool. Trust me, this will look much cooler with other functions. Now, moving on to the nth derivative of sine. You might have learned that the derivative of sine is cosine, and that the derivative of cosine is negative sine, then negative cosine, and then repeats back to sine. Sure, we already have a pattern, but there's not a neat way to make this into a formula for its nth derivative, right? You also might have learned that the cosine of an angle is the same as the sine of the complement of that angle, but this won't help us too much either. The trick here is to look at the graphs. The graph of sine looks like this. Now, cosine, its derivative, looks like this. I'll remove the graph of sine so that you can see what happened. Now I'll graph the derivative of cosine, negative sine. I'll now get rid of cosine. You probably see where this is going, and I'll do it one more time. The derivative of negative sine is negative cosine. You probably noticed that for each derivative, the wave shifted to the left. Also notice that they always move the same exact distance towards the left. Specifically, that distance is pi over 2 radians. One neat trick to move a graph to the left is to add a constant to the input of the function. If we add pi divided by 2 radians to the input of sine, it would become sine of x plus pi over 2. Conveniently, when we graph this new function, this is the same graph as its derivative, cosine. The reason why this works is that we are tricking the original function, sine, to read its input as if it was pi divided by 2 to the right, and move that input to the spot of x, making the entire graph shift to the left by a distance of pi divided by 2. If you want the derivative of cosine, then just add another pi over 2 to the input, which will make the second derivative of sine, sine of x plus pi. This pattern continues for the nth derivative of sine, and therefore our formula for the nth derivative of sine is sine of x plus n times pi over 2. Cool, since we have a formula for the nth derivative of sine, we can plug it into the Taylor series, and this one looks really cool. Now, for the final, the most complicated, and my favorite, we are going to tackle the nth derivative of 1 divided by x. This one, like the derivatives of exponentials, will be tackled numerically, meaning I won't use many pictures such as graphs. Calculating the first few derivatives of 1 divided by x, we get negative 1 divided by x squared, then 2 divided by x cubed, then negative 6 divided by x to the fourth, then 24 divided by x to the fifth, and so on. There are 3 things to notice. First of all, the most obvious thing is that for each derivative, the exponent gets raised by 1. Second, notice how the derivatives alternate from being positive and negative. Finally, notice how the numerator seems to increase in a factorial pattern. With further insight, and if you calculate the derivatives yourself, this is caused by the power rule. For the formula, we'll deal with each inference step by step. For the first one, we can write the exponent in the formula in terms of the nth derivative, n. But be cautious, since the denominator in the formula is not x to the n. Side note, you always count the initial function as being the 0th derivative of itself. This denominator is actually x to the power of n plus 1, since the 0th derivative of 1 divided by x is 1 divided by x to the first, not 1 divided by x to the 0. Okay, 1 down, 2 to go. For the second notice, the derivatives alternate from being positive and negative. Well, there's actually a really easy way to account for this. All we need to do is multiply the formula by negative 1 raised to a power of either n or n plus 1. This way, as you increase n by an integer, it will either multiply the formula by -1 or +1. To match the derivatives, the exponent of -1 has to be just n, not n plus 1, and see if you can verify why this must be the case. Alright, for the final notice, this one is quite the simplest. Since the numerator rises in factorial terms, an actual guess that the numerator is n factorial is actually correct. You can also verify this yourself, and if you don't know, 0 factorial and 1 factorial both equal 1. So that's it. This is our formula. N factorial divided by x to the power of n plus 1, all times -1 raised to a power of n. If we plug this into our Taylor series, not only do we get some unexpected cancellation with the factorials, but this one is my favorite so far. So to recap, we came up with the formula for the nth higher order derivative of an exponential by taking a look at how the natural log of the base of the exponent accumulates. Next, we figured out the higher order derivatives of sine by looking at how its derivatives move the graph to the left. Finally, we identified 3 key things with the pattern for the higher order derivatives of 1 divided by x, and using them came up with the formula. And that is all I'm going to cover for this video. I hope you learned something, whether it was not to give up like what I did, or how derivatives are not random. With that, I encourage you to try to find other patterns with the derivatives of other functions. If you want to learn about Taylor series, 3Blue1Brown has a video on it on his calculus series. Thank you, Desmos, for the inspiration, and thank you for watching. Goodbye.